Welcome back to part 2 of special power supplies. We just finished off with UPS and generators. Now we're going to move on to these electronics power supplies, specifically switch mode power supply. I'll start off with the admission. I don't know a huge amount about switch mode power supplies, so most of this will just be me reading the PowerPoint slides and do a bit of Googling if you want to know some more information. But mainly we're concerned, as I said in the last video, about safety side of this. So let's talk about what is the switch mode power supply, how does it work, what is it for, and then what are our safety considerations around it. So the most common type of power supply today is a switching supply. These units use pulse width modulation to regulate output. Suppliers today employ several different PWM circuit configurations. In all cases, the PWM logic signal drives the switching power transistor, and the power transistor drives the load. The switching transistor turns on and off rapidly, producing a chopped DC voltage. The chopped DC voltage is fed to a transformer which converts the pulsating DC to high frequency AC. This AC then is fed to a second bridge rectifier which produces the final DC output. The sensing circuit continuously monitors the output voltage, adjusting the switching duty cycle to maintain a constant output voltage. Cool story. Okay, so what's happening here? A couple of things. What we have is a transistor that is switching on and off. Remember when we did the, we made a small dimming circuit, light dimming circuit with an SCR. We had a couple of components, a capacitor and a resistor in there, variable resistor. And remember that when we changed that, we were able to chop parts of the waveform off. So the more of the waveform we chopped, the less of the waveform went through to the light, and therefore the lower the average voltage that was received by the light, and so it would be dimmer. So this switch mode power supply is essentially taking advantage of the same thing in order to give us really clever voltage regulation. So we can chop up the waveform to give a precise value of voltage and change that voltage, pretty quickly. So the more I chop out of the waveform, the lower the voltage is going to be. The more of the waveform I allow through, then the lower the voltage output would be. Switch mode power supplies, or switching power supplies, are more efficient than series regulated ones because little power is dissipated in a switching transistor. Right, so when we talked about DC power supplies a month or so ago, the types of power supplies we had, or the types of regulations we had in there, remember we had like inductors or resistors in series with our load to regulate the voltage. Those inductors and resistors are going to dissipate some power, so they're going to cost us some money to run them when we get nothing out of it. All that does is regulating our voltage. In this case, we're just using a transistor that switches on and off, so in terms of the power used by the device itself and to do the regulating is pretty low. Switching supplies are physically smaller than series regulated types because components operating at a switching frequency, typically 20 kilohertz, so we're switching really fast at high frequencies, are much smaller than those used in non-switching supply operating at 20 to 60 hertz. These power supplies are well suited where compactness, efficiency and moderately accurate regulation is required. But switching type power supplies are electrically and sometimes audibly noisy, thus they are unsuitable for powering circuits that are sensitive to electrical noise unless those circuits are filtered and shielded. Finally, switching power supplies are generally more costly than underside power supplies. Right, so we don't need the big gear inside there, we don't need big transformers and inductors and stuff like that. We just have small resistors doing that job, so that means that these things will be smaller and cheaper usually. Yeah, that makes them pretty good for little things like cell phone chargers and stuff, right? And we have moderately accurate regulation, so we can get changing output voltage depending on whatever our factors are. One of the disadvantages, as it says there, we get noise on circuits. So every time we switch on and off, if you think every time we switch a light switch on and off, we create an arc, right? So even switching in a transistor, we're going to get spikes and stuff like that, harmonics perhaps. So we're going to create a noisy voltage, which means it's just a low quality power output compared to other types of power supply. Advantages and disadvantages. The main advantage of the switching power supply is greater efficiency than linear regulators because the switching transistor dissipates little power when acting as a switch. Other advantages include smaller size and lighter weight from the elimination of heavy line frequency transformers and comparable heat generation. Standby power loss is often much less than transformers. Disadvantages include greater complexity, the generation of high amplitude, high frequency energy that low pass filters must block to avoid electromagnetic interference, and ripple voltage at the switching frequency and the harmonic frequencies thereof. All I'll say about that is, so we're going to create, by doing this, we're going to create some EMI, electromagnetic interference. We know about what the issues with that are. So when we create it, we're then going to have to add extra circuits to get rid of it. So that makes this whole thing a little bit more complicated than it would otherwise need to be. Very low cost switch mode power supplies may couple electrical switching noise back onto the mains power line, causing interference with AV equipment connected to the same phase. Non-power factor corrected SMPSs also cause harmonic distortion. So again, it's just about the quality of our power. Warning. Okay, the safety stuff. As I said before, safety. This module to me is about safety. It's about being aware of these different types of power supplies because of the issues that safety issues that surround them when we come across these in the wild. Particularly if we're not aware of them, we've never come across them before. We've talked about obviously UPSs and generators. So with these ones, the main filter capacitor will often soar 320 volts, up to 325 volts, long after the power cord has been removed from the wall. Not all power supplies contain resistors that discharge the capacitor. Any contact with this capacitor may result in a severe electric shock. The primary and secondary sides may also be connected with a capacitor to reduce EMI and compensate for various capacitive couplings in the converter circuit where the transformer is one. This may also result in electric shock in some cases. So capacitors, right? We're going to have big capacitors in these things. We know that capacitors can hold energy. 320 volts, 325 volts. If you think about that for a second, you'll probably realize that 325 volts is the peak voltage on our 230 volt RMS supply. So if we charge a capacitor up to the peak of our waveform, then it could sit at 325 volts, which would be very dangerous to us. So when we're dealing with switch mode power supplies, any type of enclosed power supply, let's be aware of this, the stored energy that may remain after we have unplugged it. Okay, applications of an SMP switch mode power supply. Security systems, machine tool productions, AV products, support supplies for PLCs, personal computers, mobile phone chargers. So a lot of modern electronic devices will have some sort of switch mode power supply, so we need to be aware of these things. Right, self-oscillating power supply, another type of electronics power supply. Another type of electronic power supply that I also don't know that much about. Also known as a ringing choke converter or self-oscillating flyback converter. Wow, so there you go. If anyone ever says, hey, have you got a self-oscillating flyback converter? Now you'll know what they're talking about. It's a type of flyback converter, switch mode power supply, which does not require a separate oscillator, but the switching of primary current is achieved by a built-in self-oscillatory action. Self-oscillating flyback converters can be divided into three types. Fixed on-time, variable off-time, which results in very low switching frequencies at light load. Fixed off-time, variable on-time, with low switching frequency with maximum load. Variable on and off-time with variable switching frequency but less than the two previous types. The self-oscillating flyback converter is a popular circuit for cost-sensitive applications due to its simplicity and low component count. The self-oscillating flyback converter technique is now widely used in mobile phone battery chargers, electronic ballasts, DC to DC converters, and other applications with similar demands. Also called a ringing choke converter because the regenerative signal for oscillation comes from the ringing of the transformer choke. The basic circuit diagram of a self-oscillating flyback converter is shown below. Well, it looks pretty basic, doesn't it? We have a transformer here. We've got a transistor, a resistor, a diode, a winding. I don't know what any of it does. So why don't we read about it? When the input voltage is applied, base current flows to the transistor through the starting resistor. When the transistor is turned on, the transformer's primary winding is excited and the transistor is forward biased by the voltage induced in the base winding. As a result, voltage induced in the base winding increases with the raising of collector current and the transistor is turned on quickly. Now the transistor shifts into the active region and the collector voltage increases. The voltage of the primary and base windings drop and the transistor is turned off. As a consequence, energy stored in the transformer is transferred to the load through the rectifier and filter components on the secondary winding. The circuit repeats this switching process with an output frequency that varies with the input voltage and the state of the output load. The advantages: the component count is very low and thus the converter can be made inexpensively. A complete energy transfer, discontinuous mode, self-limiting operation for overcurrent and magnetic saturation. Disadvantages are: the coupled inductor requires 3 windings which increase its cost. The converter should be run with at least 10% of load. Okay, we're going to pause there. That will be part 2. I didn't do a very good job of dividing this video up, did I? And the last one was about 40 minutes and this one's like 12. Nevertheless, the second digit of your code is 8. Second digit of your code for the test is an 8. Alright. Happy? Don't answer, I can't hear you.